NGC 2217 is a galaxy that has been hitting the media in recent, not just because of the glamour and sparkly nature of the object, but mainly because it was imaged by the Hubble telescope, a space telescope that has insane capabilities with capturing both scientific data and some of the most gorgeous images that have ever been produced. There's more to the story of this galaxy, though, such as the fact that it lies over 70 million light years away, has produced one supernova, and the fact that it is a galaxy in transition. So today, we're diving deep into this galaxy. This is the story of NGC 2217. I hope you enjoy. NGC 2217 is a peculiar galaxy located 73 million light-years from Earth in the constellation of Canis Major. In the night sky, the galaxy can be found to the upper left of Farood and to the lower right of the Little Beehive cluster. Like many galaxies in the local universe, and even some in the more distant universe, NGC 2217 has an extensive observation history, and while it may not be as extensive as the likes of NGC 7469, NGC 6946, or Messier 74, it hasn't been completely untouched either. To show this, let's turn back the clock. NGC 2217 was discovered by the English astronomer John Herschel on January 20th of 1835, which for context was about 189.5 years prior to this upload date and 9.5 years prior to the discovery of Neptune. 53 years after the discovery of the galaxy, the Danish astronomer John Dreyer would observe it, describing it as being very bright, small, round, suddenly brighter in the middle, and modeled but not resolved. Like many galaxies, observations of NGC 2217 were pretty quiet up until the mid-20th century, when a lot of characteristics would become known. The 1960s, 80s, and 90s would be the highlights of the century in my opinion, as much of the physical characteristics that we know of about the galaxy would come from papers like the Reference Catalogue of Bright Galaxies by Gerard de Vaucouleurs in 1964. Wow, I probably pronounced that just horrendously. The Revised Shapley Ames Catalogue of Bright Galaxies in 1981 by Alan Sandage, and Volume 1 of the Carnegie Atlas of Galaxies by the same author in 1994. The 80s and 90s were significant as well when referring to other characteristics of the galaxy, with the gathering of photometric data across optical and infrared wavelengths as well as physical diameters within the same range of wavelengths being notable feats of that time period. The collection of observational data for NGC 2217 would ramp up as the 21st century began, as the Hyperlita Atlas, the 2-micron All-Sky Survey, the High-Pass Catalog, and the 6-degree Field Galaxy Survey would begin pumping out loads of data, whether it be photometric data, physical characteristics, angular sizes and diameters, and distance measurements. The 2000s and the 2020s stick out to me the most because of two reasons. The first is because the high-pass catalogs would identify NGC 2217 as a neutral hydrogen source, which is a source in interstellar/intergalactic space where atomic neutral hydrogen is present, and the second is because the Chandra source catalog would identify the galaxy as an X-ray source in 2020. Apparent magnitude is defined as the apparent brightness of an object as viewed by an observer from Earth. This is normally measured through specific bandpasses, or ranges of wavelengths in various portions of the electromagnetic spectrum, such as the ultraviolet, visible, or infrared. The most commonly quoted bandpass in common discussion of an object's apparent magnitude is the visual band, or the V-band. This is because the V-band is the bandpass that the human eye is most sensitive to, as it displays at a mean value of 551 nanometers. In the case of NGC 2217, it has an apparent magnitude of 10.4 in the V-band, making the galaxy impossible to see with the naked eye, but visible with the aid of a telescope with an aperture of 15 centimeters or greater. Alright, great. So we have the apparent brightness for one whole bandpass. Whoop-de-fucking-do. So how bright is NGC 2217 at different wavelengths? At their peaks, the visible spectrum reaches a magnitude of 9.78 in the R band, the ultraviolet reaches 11.86 in the U band, the near-infrared reaches 7.09 in the K band, and the mid-infrared reaches 5.22 in the W4 band. Okay, so we know how bright the galaxy is in the night sky in wavelengths that the human eye is most sensitive to, and we also know how bright it can get in areas of light that we can't see. But how bright is the galaxy itself? Or more specifically, how luminous is it? Well, it's more luminous than the Milky Way, I can say that much. The luminosity of a galaxy in the context of photometry is dependent on two things: its apparent magnitude and its distance. The reason that distance is important is because if you have two objects that are at different distances from Earth, but their magnitudes are the same, then the object that's farther away is going to be more luminous than the object that's closer. The relationship between apparent magnitude and distance is used to find the absolute magnitude, or what the apparent magnitude of an object would be if it was 32.6 light years from Earth, which can then be used to find the luminosity. In the case of NGC 2217, it has a luminosity of 27.4 billion solar luminosities in the V band. While this makes the galaxy 52.2% more luminous than the Milky Way, a galaxy of its kind being 27 billion times more luminous than the Sun isn't uncommon at all, especially given its size. This is merely its luminosity in the V band though, meaning that this value is going to be different depending on the bandpass that we're looking at. Like for example, the peak luminosity of NGC 2217 in the visible spectrum is about 48.6 billion solar luminosities in the R band, whereas the peak luminosity in the ultraviolet spectrum is much lower, at 7.15 billion solar luminosities in the U band. In the beginning of the video, I said that NGC 2217 is a galaxy in transition, but what do I mean by that? Simply put, the galaxy structure is, well, interesting, to put it lightly. So let's start from the beginning. The galaxy has a central bar, which is important in the development of a galaxy as it can funnel gas towards the galactic center, in turn helping feed the central black hole, which we'll talk more about later, or aid in star formation. Interestingly enough, though, there isn't one bar here, but instead, there's two, with the second one being hidden within the center of the first one. The longer/outer one is likely the one that formed first, with the second one forming later due to gas funneling from the outer portions of the galaxy into the center and forming stars. This interstellar gas and stars would then become the basis of the second bar. Double-barred galaxies are similar to single-barred galaxies because they also funnel gas from the outer portions of the galaxy into the center. But the main difference between the two systems is that the double-barred galaxies are more efficient in funneling interstellar gas into the center, which is helpful in aiding in star formation and feeding the central black hole. On the ends of the bar system are enci, which are a kind of enhancement on each side of the bar. They can look like handles on each end of the bar, which is why I like to personally call them the love handles of the bar system, and are present not just in galaxies, but in nebulae as well. Surrounding the bar is an oval-shaped ring that is visually smooth. In some images, it appears more yellowish-white, and in others, it takes a more reddish hue, both of which indicate that this region is filled with older and cooler stars, perhaps ones that have a spectral type of M, K, G, or F. The smooth/smeared-out nature of the ring, as well as the faint nature of it in several images, suggests that this region has either ceased star formation or is on its way to. This is something that is characteristic of lenticular galaxies, which is a type of galaxy that is the intermediate stage between spirals and ellipticals. Surrounding the oval ring are two tightly wound spiral arms that form a near-complete ring. The arms themselves have a lower surface brightness, are poorly defined, and take on a bluish hue, indicating that they are filled with younger, hotter, and more luminous stars, perhaps ones that have a spectral type of A, B, or O. Within the arms are young and hot star clusters, knots, and interstellar dust. One of the most prominent features of this galaxy is, by far, the galactic center. Now, part of this is because of the double bar system, but the other part, without a shadow of a doubt, is due to the nucleus. The nucleus takes on a bluish hue, which, much like the spiral arms, is indicative of hot, young, and luminous stars being present there. NGC 2217 is an active galaxy, which is a type of galaxy that is generally more luminous in the center and is emitting a lot more energy than what stars alone would normally do. Galactic activity comes in all different kinds of flavors, and with NGC 2217 specifically, it falls under three of those flavors. To begin with, it is a liner galaxy, which is a type of nucleus that tends to emit radiation from elements in a weakly ionized or neutral state. Moving on, the galaxy is also a Type 2 Seyfert, which is a kind of galaxy that is characterized by a quasar-like nucleus, especially in the infrared wavelengths. While these two kinds of galactic activity have differences in their own right, the one thing that they have in common is what can cause them to come into existence: an active galactic nucleus, the third flavor of galactic activity for NGC 2217. An AGN is a compact region at the center of a galaxy that emits significant amounts of energy across the electromagnetic spectrum, more so than what stars can do on their own. This is because AGN are generally powered by a supermassive black hole, which is something that applies to NGC 2217. The mass of the black hole itself is about 1.3 million solar masses, which gives it a diameter of about 7.6 million kilometers, equating to a size about 5.5 times larger than the diameter of the Sun. So with everything said, what is the physical classification of NGC 2217? Because if you've noticed, I've not actually given the physical classification, I've only hinted at what it could be. Well, the conclusion that myself and several sources have come to is that the galaxy, more likely than not, is a double-barred spiral that is in the process of becoming a lenticular. The evidence supporting this comes from information discussed prior, such as the spiral galaxy characteristics when it comes to the structure of the spiral arms and the contents within them, and the lenticular galaxy characteristics when it comes to the central ring. To add on to the legitimacy of this conclusion, surveys in the past have classified NGC 2217 as a transition between a spiral and lenticular galaxy, which has caused some physical classifications to look a little something like this. Everything that we've covered up to this point has been interesting in their own right, such as the transitional nature of the galaxy, the presence of a million solar mass black hole, or the recent attention it recently got due to Hubble imaging. But for me, that stuff wasn't what got me initially interested in this topic. Rather, it was the supernova that sparked the flame, as I was able to learn about a subclass of supernovae that I didn't know much about at the time. NGC 2217 only holds one supernova, SN 2017 FCW, and it, like many others, has a story of its own, so let's dive into it. The story begins on August 9th of 2017, when the supernova was initially detected. At the time of its discovery, 2017 FCW had an apparent magnitude of about 17.1, which meant that it had a high luminosity, at 53.8 million solar luminosities. But just like the galaxy that it was home to, it was far too dim to be seen with the naked eye. As time began to pass, the supernova would increase not just in apparent brightness, but in luminosity too, digging even further into the millions and eventually crossing the 1 billion solar luminosity mark. It would eventually hit its peak brightness on August 22nd of 2017, when it reached an apparent magnitude of 13.2 in the B band and a luminosity of 1.2 billion solar luminosities. This made it impossible to see with the naked eye, but at the time of its peak, it was visible with the aid of a telescope, so long as it had an aperture of 25 centimeters or greater. After peaking in brightness, 2017 FCW began decreasing in brightness, as all supernovae do, and eventually, it would just fade away, becoming a shell of what it once was. So what kind of supernova was this thing? And more importantly, what were its characteristics? Ironically enough, 2017 FCW, much like its host galaxy, was classified as a transitional object between two subclasses of a supernova, those being a traditional Type 1A and a 1991 BG-like 1A. So what are these two types of supernovae? Type 1a supernovae are a kind of supernova that are caused by the explosion of a carbon-oxygen white dwarf in binary star systems that go over the critical mass limit of about 1.4 solar masses due to processes like merging or the accretion of mass via a donor star. Now, that's great and all, but how can you tell each subclass of the supernova apart? Typically, the main differences come from discrepancies in their light curves as well as their spectroscopic data. In the case of SN 1991 BG-like 1A supernovae, some ways that they differ from traditional 1A supernovae in their light curve is that they tend to be dimmer, decline in luminosity at a faster rate, and can also be either redder or bluer in some bandpasses of light. When it comes to the spectroscopic differences, they tend to have an unusually deep and wide trough at wavelengths around 420 nanometers, have a strong ionized silicon absorption line at a wavelength of 597.2 nanometers, and produce a fraction of the amount of nickel that traditional 1A supernovae do, with an average nickel production of about 0.1 solar masses. So with that said, what is 2017 FCW like? When looking at its photometric light curve, the supernova is very red, much redder than traditional 1A supernovae. In the paper that this information was pulled from, the authors note that it's even redder than the comparison supernovae that they used even after the reddest color. On the other hand, 2017 FCW is also very blue, with it being significantly bluer than 1991 BG-like 1A supernovae at its peak brightness in the B-band. Post-B-band peak, the supernova would experience a rapid decline in brightness, dimming by 1.6 magnitudes in the first 15 days. Okay, so we've got the photometric data covered. We see that it is very red, very blue, and it decreases in brightness at a rapid rate after it peaks. But what does the spectroscopic data look like? 2017 FZW has very strong ionized silicon and neutral oxygen features, in particular, ones that are much stronger than traditional 1A supernovae, as well as having a prominent ionized titanium absorption feature. Specifically, the titanium absorption feature is significant as it strengthens the classification of the supernova as being 1991 BG-like. Remember when I briefly talked about nickel production earlier? This is something that 2017 FCW does, and in total, it has produced 0.18 solar masses of it, which puts it at about average for 1991 BG-like supernovae. We've gone over a lot in this video. We've talked about apparent magnitude, luminosity, physical characteristics, and a supernova. But one major thing that we haven't covered is the galaxy's physical size. How big is this doohickey in the sky? While the general consensus is about 100,000 light-years, which to be clear is the diameter that should be used in common conversation to avoid confusion, the true answer to this question is dependent on the method used to measure NGC 2217's diameter in the first place. Generally speaking, the gold standard for measuring a galaxy's diameter is through the D25 standard, or the measurement of a galaxy's size down to a surface brightness of magnitude 25 per square arcsecond. This method of measurement that bases galaxies off of apparent surface brightness is known as their isophotal diameter. Using this method, NGC 2217 has an angular size of 302 arcseconds, or 83.9 thousandths of a degree, giving the galaxy a diameter of about 107,200 light-years at its present distance, making it 22.6% larger than the Milky Way. Obviously, this isn't the largest that the galaxy can get with isophotal diameters, as when using alternative methods, it can reach sizes of up to 173,860 light-years in the visible spectrum, and 156,330 light-years in the infrared spectrum, again using its present distance. While the isophotal method is the predominant method used to measure the sizes of a galaxy, there's another significant one that I want to discuss, known as the effective diameter, aka the half-light diameter. The way this one works is pretty straightforward, as all it does is measure the diameter of the galaxy to the point where half of its total light is emitted. Using this method yields an angular size of 164 arcseconds, or 45.6 thousandths of a degree, which gives NGC 2217 a diameter of about 58,240 light-years. This is a stark difference when comparing to the D25 method. However, that is to be somewhat expected, as this is a different method of measurement that we're using here. Similarly to the isophoto method that we discussed earlier, this one also has various sub-methods that are also used. The most common ones measure the effective diameter of a galaxy at the points where 70, 80, and 90% of its total light is emitted, and in the context of NGC 2217, the size of the galaxy ranges from 82,260 light-years to 151,420 light-years using these alternative methods. Due to the expansion of the universe, NGC 2217 is a redshifted galaxy. This means that instead of approaching us, it is moving away from us. This causes the distance that light traveled from the galaxy to reach Earth and the current distance that it lies at to be two different values, which can be expressed in a redshift value. The galaxy has a redshift of 0.00505, which gives a heliocentric velocity of 1,514 kilometers per second, or 5.45 million kilometers per hour, and a present distance of about 73.2 million light-years. This corresponds to a 218,000 light-year distance increase, which is a 0.3% increase over its light travel distance of 73 million light-years mentioned at the beginning of the video. NGC 2217 is a weird galaxy. There's no doubt about it. From the broken ring shape that the spiral arms take, to the lenticular-like properties of the interstellar dust within the galaxy, to even the interesting nature of the supernova that's been observed, this galaxy is one to remember, and for good reason. While it may not be a titan of a galaxy like IC 1101, it does outclass the Milky Way in several statistics, such as its luminosity and diameter as discussed earlier. Despite how fascinating the galaxy is, though, it isn't very well known among the general population and is most certainly under-discussed because of it. And I hope that with this video, this could shake things up a little bit and get people talking, because this galaxy absolutely deserves more attention than it's getting. This was a deep dive into NGC 2217. Thank you for watching.